Welcome, thank you all for showing up. I'm not Dana Bauer, I'm Sara Safavi. Dana Bauer was supposed to be here. Unfortunately, she fell ill today, so she is currently either in her hotel room upstairs, hopefully sleeping, or at the doctor. So I'm going to be doing my best to walk you guys through it. Please be a little bit patient with me since there's just one me and a lot of you. But if you do have trouble and need help and I don't immediately see you, feel free to yell, be really big with your waves and all that, because I might miss you. But yeah, I'm Sara Safavi. I'm a software engineer at a company called Planet. And just to make my ego feel good, how many people have heard of Planet? Awesome. How many people have heard of Planet before you signed up for this tutorial? Hey, double awesome. Cool. That's really neat. Yeah, so for those of you that aren't familiar, Planet used to be called Planet Labs, also known as Planet Labs. Basically what Planet does, hang on a second. All right. Basically what Planet does is they're a mature startup, I guess you could say, that builds and launches tiny satellites. And they're not quite this tiny, but this is like a 1/64 scale model. So they're basically the size of a large shoebox, or I like to say a small corgi. And they're like, I think, 8 kilograms. So Planet builds and launches these tiny satellites that look like this, more or less. And what they do is they do Earth observation imagery collection. And I'm going to talk a little bit more about what exactly that means later. But basically, the satellites are capturing imagery of the entire Earth's landmass every 24 hours. So we've got the entire Earth being imaged at about 3-meter resolution every day. And that's really amazing and unique, and that's part of why I'm interested in working at the company as a geospatial software engineer interested in spatial data. So today we're going to learn a little bit about Earth observation and satellite imagery in general, broader than just the idea of Planet's data, but we're going to use Planet's API to access data because we can get data that's not only Planet's data with one API, and so it's easy just to have one system to download all kinds of data. To give me a baseline, anyone in here already worked with or familiar with satellite data? Okay, why are you here? No, I'm kidding. Cool, that's good. If you have no experience with satellite data at all or geospatial raster data of any type, and if you don't know what that means, that's cool. That's fine. We're going to start basically at the beginning. I'm going to give you a quick and dirty introduction to what kind of data we're going to be working with. Then we're going to take a look at some of this data in a graphical interface, that QGIS program that hopefully y'all installed. We're going to use that to look at some data. And then in the second half of this tutorial, after the break, we're going to use Python to work with satellite data. So we'll start out by acquiring it. Hopefully some of us can use the API, but there's a demo data download that you all have been working on in case the API gets bogged down or this room's Wi-Fi gets bogged down. And then we're going to start actually manipulating satellite data and get interesting information out of it. So before I get started, anybody have questions? Yes. Yes. Yes, there is. I'm going to get to this in a second. I'm going to go ahead and pass these around. These are blank USB sticks. I did not have time to put the data on it. However, you can take one, copy data on it, and hopefully it helps. I really hope there's enough USB keys to go around. If there's not, I will buy you guys a coffee if you don't get a key because I feel really bad. Yes, question. So if you copy paste that entire HTTP line with the token, it doesn't, what does it? Oh, you shouldn't need Wi-Fi, it's a local host. You could use different ports if for some reason that one's in use. You could change the 8888 in your run command. Thanks. Dude back there's got you. Awesome. Thanks, Alex, by the way. He's an awesome person who is helping us at the last minute. Okay. What's that? Oh, no. Okay, there's way fewer than I thought. I was told there was 40 in that bag. Yeah, I owed like a lot of coffee. I'm sorry. I did not count them. All right, if you don't get a USB key, definitely please come get swag and stickers. People that didn't get USB keys get first pass. I'm real sorry. I thought there was 40 in there, and I was hoping that would be enough. Talk to me later if you really want one of those. I'll try to get one mailed to you. Okay, so any other questions before we get started on satellites? Yes? Okay, so couple weeks ago, sometime in June, you guys got an email from SciPy organizers, and it had information about prerequisites. The prerequisites were Docker, a clone of this repo, I believe, and QGIS. I believe that was the first set of instructions you got. You got a reminder about that also from SciPy organizers a couple weeks after. Then last week you got 2 emails from me, so you can search my name in your inbox, that has additional information about going ahead and getting Docker built. And then I've been, if you're in the Slack channel for our thing, our tutorial, there's a bunch of information. If you run into problems, you might be able to search somebody else had the same problem. So I'll say it one more time for the benefit of the video and the class and all that. If you are starting from scratch right now and don't have anything set up from that prerequisite list, you might not, you probably won't be able to get it done in time to fully participate in the code when we get to that part. You're still totally welcome to stay. It's just there's a lot of things that are a pain to set up, which is why we use the Docker config. And I can't guarantee that you'll get it done, you know, in the next few minutes. But Godspeed if you're trying. Hopefully most of you have it done so that we can write some Python in this class at SciPy. All right, a little bit about satellites and Earth observation. I'm not going to go too deep on this. I just want to give you a basic idea of what is over our heads right now. So like I said, Planet has a bunch of these teeny tiny sats. Planet has about 150 of them in sun-synchronous orbits right now, taking images of the Earth. But beyond Planet, there's a bunch of other satellites out there. Some commercial, a lot of government, and a lot of Earth observation sensors of different varieties. Anybody familiar with Landsat? Most people have heard of it. Landsat is the longest running Earth observation satellite program. It started in, I think, 71 or 72. It had a different name back then than they renamed it, but it's the same stuff. So right now it's NASA and the USGS that run it, and there's 2 of them up there, Landsat 7 and Landsat 8. Landsat 9, I think, is coming next year or the year after. But yeah, that's the longest running Earth observation program. It's pretty cool. And that's US Gov, so all of that data is free and available to everyone. Sentinel, the Sentinel program, I'm less familiar with the numbers there, but that's the ESA, the European Space Agency. So there's Sentinel-1, Sentinel-2, and probably others that I'm not familiar with. But they are also government run. The data is accessible in different portals, obviously, than you would get US Gov data, but it's also out there. And then, like I said, Planet's got 150. And there are other commercial, private, non-government satellites out there. Digital Globe, for example, runs satellites that does Earth observation and so on. So different types of sensors. Again, I'm not going to go deep on this, but the general idea that you should be aware of is when I'm talking about satellite imagery, especially in the context of this class, you have to realize that satellites capture more than just light that's visible to your eye. So when we talk about imagery, we think about like cameras on our phones, for example. But that's only capturing what you can see with your eye, so red, green, and blue color. But when a satellite sensor captures an image, it can see farther into the light spectrum than we can, so it captures more light. So there are a number of different bands of light spectrum that are captured, but today we're going to be talking about red, green, blue, and also near infrared. So near infrared is really commonly used in satellite data analysis, remote sensing, especially if we're talking about natural features, vegetation, versus unnatural man-made, like, for example, roads or buildings. Near infrared light makes it really easy to distinguish those things on a satellite image because of how much near-infrared light is absorbed or reflected by the type of thing on the Earth. So again, you can go down a Wikipedia rabbit hole for days on this if you're interested, and there are a lot of cool things out there to learn more about light spectrum and the type of sensors that are available on satellites, but just the TLDR is like you can capture more with a satellite than you can with your camera on your phone, like beyond what your eyes can see. And that's part of why Earth observation science and the act of creating Earth observation data can be so useful to us. But I guess I should define Earth observation data. I've said that a lot, but you're like, what exactly does that mean? It's probably pretty straightforward. I mean, you're thinking about it, it's data that has to do with observing the Earth. And that's basically it. But when we talk about Earth observation data, we're talking about data collected from a distance over the Earth, which due to the shape of the Earth means that it's going to be either flying over the surface or in orbit. So Earth observation data is going to be captured usually by satellites, also could be by airplanes that fly with cameras, excuse me, cameras capturing imagery, that sort of thing. But we're talking about data sensed about the surface of the Earth from a distance. Yeah?
So is there a difference here between airborne, planes, and satellite? Is there like a discriminator? Or if your sensor were on an airplane that was extremely high, would characterize as satellite data?
No, we would categorize it as remotely sensed data or Earth observation data, but satellite data is captured by satellites, which are spacecraft in space orbiting the Earth, versus an airplane. But the sensors could be similar, and the type of data captured could be similar. For the most part, we're going to focus on processing of satellite imagery. Some of those steps cross over to, for example, aerial imagery captured by an airplane. And I'll get into the similarities in a minute when we talk about raster versus vector, but that is a good question. In fact, let's go on. How satellite data is captured. I talked a little bit about sensors already. I talked about satellites being spacecraft orbiting the Earth. Characteristics of satellite data. It can answer the question you're asking. Satellite data is just another flavor of what we call raster data. So if you've anybody worked with geospatial GIS data at all? Okay, so you're familiar probably with the terms raster versus vector. Raster data, if you're not familiar, is just anything that's an image made up of pixels, just like a JPEG that you open up when you download cat GIFs and open cat memes and stuff like that. Rasters are pictures. Vectors are vector data made up of points, lines, and polygons. So it's the more geometric type of data if you're more familiar with thinking of geometry versus geospatial data. But satellite data is a type of raster data. Specifically, it's a type of geospatial raster data. And it's unique in those respects in that as raster data, it's made up of pixels. It's not made up of points, lines, and polygons. As geospatial data, it's not the same as a cat meme that you download and as an image. It has location information attached to it. So cat GIFs don't have location information. Satellite images know where they are, or where they are in relation to the surface of the Earth. So they have spatial information tied to them. They have a coordinate reference system, and they are located somewhere on the surface of the Earth. That's the unique quality of geospatial data. That's the only unique quality of geospatial data. So it's just data that has location information attached. So today we'll learn how to work with that specific type of raster data with Python. And we will try to stay a little bit on the surface of the morass of coordinate reference systems and projections, but just know that they exist and nobody understands them, and they have to do with projection or location information. Any questions so far? So far, so good. All right, cool. Quick check-in. Is the data still going around on our pin drive? Awesome. Great, good. Anybody having any trouble downloading it, let me know. I'll try to copy it off of my laptop and give it to you. But sounds like we're good. Okay. Oh, wait. A little bit about geospatial data basics. I talked about raster versus vector. I talked about what makes spatial imagery special. And I'm going to talk a little bit more about metadata. So I told you that spatial information has location information of some kind attached to it. It has other information attached to it in what we call the metadata. You're all probably familiar with the concept of metadata as far as files go. Specifically in GIS data, metadata is going to contain generally some of the same things no matter what the data set or data type is. So it's probably going to contain its coordinate reference system or projection information, so you know the mathematical formulas to apply if you want to transform the coordinates into another projection. It's going to contain, for a raster, it's going to have, for example, the extents, like how big, how much space does this image cover on the surface of the Earth? How many pixels is it? That sort of thing. And this is all useful to us if we're working with it. And when I get you guys using the Python notebooks, we're going to mess with that metadata to learn more about the information in the image. So I wanted to get everybody looking at an image using QGIS. So let's see if this actually works. If you've got data of any kind from that demo directory on your laptop, you should be good to go. We're going to open that QGIS thing that you guys installed, and we're just going to take a visual look at some of this data. And we're going to see if my QGIS works because I haven't opened it in a couple weeks. And I downloaded an update for it. Okay, it works. Cool. So when you've got this open, raise your hand so I get an idea of the room. What's that? Okay. I'm about halfway. Cool. Cool. Getting there. Awesome. They came with QGIS? I don't actually know what comes with it. I think it depends on where you get your installer from. So sure, if you want to. So while people are maybe opening it for the first time or finishing downloading, I'll tell you a little bit about what this program is. Anybody in here worked with ArcGIS? Okay, this is the open source version that's better than that you should use instead because ArcGIS is proprietary. But basically, for those of you that aren't familiar, QGIS is, as I said, an open source project. It's a desktop GIS analysis tool. So you can do everything we're going to do in Python today here in QGIS if you preferred, but because this is SciPy, I'm not teaching you QGIS. But it's really awesome, super convenient, and I highly encourage you, if you work with spatial data of any type, whether vector or raster, to use it or try to learn it. And as an open source project, there's a ton of resources on the internet. There's some great YouTube series, if you're into that type of learning, for getting to know it. What I've got running right now is a little bit of an old version. This is the LTS that I recommended in Slack for you Mac people. I'm running Ubuntu, so I'm just lazy. I don't have any excuse for not upgrading. But there's a newer version, and it looks a little bit different. But we'll go ahead and get started. So when you first open it, it's pretty complicated. Every button on the toolbar is already turned on. It kind of is overwhelming. You don't really know what's going on. What I want us to do is add a raster layer to our current workspace, just so we can look at it with our eyes. So on the left-hand side, there's two things here. If you hover over them, the top one is an add a vector layer. It looks like a V. It also looks like points and lines. Below it looks like a grid of pixels, says add raster layer. That's what we're going to do. I'm just going to pull up some random data. You can use whatever you have. If you have anything that's a demo data file that you acquired today that has a .tif extension, that's what we're going to open. I'm going to open a couple, actually. Just because. So far, this doesn't, seem groundbreaking. The reason I'm showing you QGIS is these raster files, these data files that you've gotten from that demo set, if you tried to open them in, your favorite image viewer, like Windows Image Viewer or whatever you use, they might not, they might look a little weird. In fact, some of you might have tried to open them because you're like, this is a geo-TIFF, I know, or it's a TIFF, I know this, I can just open it. It might look a little weird because those programs can't read all of the data that a spatial like satellite image has. So we're going to open it here in QGIS to get a better look at it. So what I've pulled open right now is what we call a visual asset type, and I'm going to talk more about that later. So this is just data that contains red, green, and blue spectral information. There's nothing contained in this particular data set that's beyond what our eyeballs can see. Excuse me. I've talked about satellite data has, for example, red, green, and blue data, or multiple parts of the light spectrum represented in the same image. I haven't really told you yet how it does that. So think about a raster image. It's a grid of pixels. Each pixel has a value. What's that? Okay. Each pixel has a value. Cool. So far, so good. What do we want to do? What do we do if we want each pixel to have multiple values? For example, a value for red light out of the red spectrum, a value for near infrared, a value for green and blue. For GeoTIFFs, geospatial raster images, we divide information into what we call bands, B-A-N-D-S. A band is essentially a layer of the same image, so we can stack information on the same pixel area on the surface of the Earth. So each pixel can have one value for each band. This image that I told you has only red, green, and blue light. It's going to have 3 bands, a red band, a green band, and a blue band. It's actually going to be blue, green, and red in the order of this image, but it doesn't really matter. The order of the bands, by the way, is something contained in the metadata that I was telling you about earlier, usually also in the documentation that comes with the imagery. So this one here that we're looking at in QGIS has red, green, and blue. Each pixel will have a value for red and green and blue. Because it's just an RGB image, QGIS does a pretty good job of representing that to us. It looks like this is, somewhere in the desert. It looks normal. The colors are right. But because those values are just numerical values for amount of light reflected off the surface of the Earth, you could technically, represent them any way you wanted here. And QGIS is something that allows you to do that. Later on, we're going to use Python to do that as well. Let's right-click on the data that you have and click Properties. We're just going to inspect it using QGIS. And I apologize, I say QGIS, QGIS, same thing. People pronounce it different ways, and I haven't caught up to the modern way of pronouncing it yet. So the first thing you can see on this general tab of the properties of the image, it's going to tell you the coordinate reference system attached to this image. Now, I know I told you I'm not going to drag you too far down this rabbit hole, but I'm going to tell you that when we're talking about coordinate reference systems, there's a universally accepted norm of using what we call EPSG codes to represent a system. So this code here, for example, is EPSG 32611, which is the WIGS 84 UTM zone 11 north, blah, blah, blah. You probably can't even see that actually, so it doesn't matter that I'm reading it because it's so tiny. But basically, the EPSG code of the coordinate reference system related to the data you have will be displayed here. Hang on a second. Let's see if I get this URL right. I did. Spatialreference.org, super useful website if you decide to go down the rabbit hole of projections and coordinate reference systems, because you can search EPSG codes by number here, and they'll come up with detailed information on what the heck that projection is. So for example, what was this one I just saw? 32611. So I'm going to search EPSG 32611. It comes up here. Let's make it bigger so you can see it. It tells me it's that WIGS 84 UTM zone 11 north. I can click it and get representations of it in different formats. So if you're working with spatial data and this is meaningful to you, this will be useful. If you're not working with spatial data frequency, this is not as meaningful. But it gives you well-known text format, gives you Proj4, JSON, different formats for the projection information. So it's a useful site. But I won't drag you much further down there. Did I see a hand or, sorry, I'm seeing things. All right. So that's something you can get out of the properties here. Let's see what else we can get actually. It tells us that it's a multi-band image. It has 3 bands, and it has automatically detected a red, green, and blue band. You could change it to different types of color schemes. You could define the values. I'm not going to do it here because it's kind of a pain, but you can define, for example, exactly what you want red to look like in this image, which we would call false coloring because you're adding a false color to represent it. Later on, we're going to do some false coloring in Python to deliberately make certain information in an image pop out visually. But QGIS, most of the reason it's useful is you download a data set, a raster file. You can't just double-click the TIFF and open it in your image viewer. It's not going to show you anything. So being able to open it in this QGIS desktop thing is how you're going to be able to take a quick look at it, sanity check, make sure, you know, I thought I was downloading an image of a desert, and this is all forest, so it must be the wrong thing. Something like that. So QGIS is what you're going to use to do that. I'm going to turn on a different layer real quick. So this image here looks a little weird. It's the same location. By the way, QGIS understands the spatial information attached to your image, so if this was not positioned on the same place on the Earth, it would not overlap like that. So if you hover over an image at the bottom of QGIS, it has, I'm pointing at my screen, that doesn't help. At the bottom of the screen it says coordinates. It's going to tell you literally the coordinates of where your mouse cursor is on the Earth. So if you're looking at a projection that has latitude, longitude coordinates, you could copy that into Google Maps, go look at it. This is not a lat-long projection. This is uses meters, doesn't matter, we'll talk about it later. But basically your mouse cursor, QGIS knows where it is on the surface of the Earth. So I've opened another image here. Same location, same exact thing. Let's turn that other one back on. Remember we were looking at the desert, there's like a city over here on the west. In fact, let me zoom in to show you that that's a city. So yep, there's a city, there's some water, there's some buildings, and then some really cool looking mountains. So I've got this other version of the same area, but it looks weird. So what I've got here is the first image we were looking at has 3 bands of information, red, green, and blue. The second image has 4 bands. It's got a near infrared band added. So the reason it looks weird right now is QGIS is assigning an arbitrary value to that near infrared value so that we can literally see it on our screens, but it makes it weirdly colored. If you know nothing about the data you've obtained and you want to look at it visually, that is something you can look for. If the colors look off, you've probably got more than just red, green, and blue band information going on here. Let me look at the properties of this. And let me not look at the properties of this because I don't remember how to find it in QGIS. But we'll do it in Python and I'll show you how to pull out that near infrared information. But basically that's all I care about you guys learning about this particular application, how to open imagery, look at it with your eyes, and get a very quick ballpark bit of information about what you're looking at. Does anybody have questions about this? Cool. So I'm going to go ahead and close QGIS for now. Close spatial reference, go back to the slides. And let's talk a little bit about getting data, which we've kind of been working on already. I'll start at the bottom. SneakerNet, it's a great way to get data. You guys have all been doing it in the last hour. You're passing around data by walking it from one person to another. Satellite imagery, geospatial raster data is huge. It's very, very convenient to just walk it over to a person versus emailing it to them. Like, that's something that happens. But beyond that, obviously, you don't necessarily have physical proximity to the people with the data that you want. There are other ways to get it. So AWS, everybody here know what AWS is? Cool, good. AWS has a great open data registry. It's a bunch of S3 buckets that host data. In fact, let me pull that up real quick. It looks like this. It has Landsat 8 data. I told you about Landsat earlier today. It has Sentinel-2 data. I told you about Sentinel from ESA. It has other things, but those are the main data sets of satellite imagery that I know of. Let me click into Landsat for you. There's documentation you can read, but basically everything is going to have a very long S3 URL. The problem with getting things out of this registry is it's a really big pain to figure out the indexing scheme and acquire lots of, search for and filter data. If you know exactly where you're going, that's cool, but it's hard to search and filter. It's just a bunch of static files in S3. But it's great because this is a mirror of all of the Landsat data. So it's free, it's available, it's easy to get. Same for the Sentinel data. So what was I going to talk about here? Oh yeah, VFS and COGS. So VFS, a virtual file system. Does anybody know what I'm talking about when I say that? Kind of, sort of? Don't worry, nobody does. S3 uses a virtual file system to serve a special type of satellite data called a cloud optimized GeoTIFF, or a COG. And the thing that's really cool about that is, as you might expect, it's optimized for the cloud. It lets you access sequentially, trying to figure out how to explain this, sorry, forgive me. Basically, you can use ranges in your GET request to obtain a part of the image. So like the beginning of the image, for example. This is really useful when you've got giant files and you don't necessarily need to get the entire thing. So Cloud Optimized GeoTIFF makes it easier to organize the data and serve it to GET requests based on a range being requested. So this data that's in S3 under the AWS Open Registry is all, as far as I know, it's all, at least the newer stuff is Cloud Optimized GeoTIFFs. There's a tool that we are using tangentially today called GDAL. We're actually using a wrapper around it called Rasterio. And it natively understands these Cloud Optimized GeoTIFF resources by URL. So the driver in GDAL, if you use GDAL, is called VSI curl. I'm not going to go too far down, well, yeah, I'm not going to go too far down VSI curl today, but I just want you to know that it's there, it exists. If the idea of Cloud Optimized GeoTIFFs interests you, it's a keyword that you can Google. It's an open source thing, lots of good documentation. But we're going to use Rasterio today, and if you were using Rasterio to fetch imagery from something that serves Cloud Optimized GeoTIFFs, it's going to use that driver in the background. Questions about the AWS registry? Cool. It's a really great resource if you need Landsat or Sentinel data. It's all there. It's all served as COGS, well, most of it. It's just hard to find what you want. But for example, if you need a test image to test something out, you'll have a reliable URL that you can use to reference it. But now I'm going to move on and talk about Planet's tools for searching for data, because I work for them and they paid for me to be here. And you guys all got API keys. I'm only going to talk about CC by SA data, so Creative Commons, licensed data, so it's all open. You have to get an API key to get it, even though it's open, just so we can limit your bandwidth. But we're going to only talk about open data today. So a little bit about how data works in Planet. Actually, I'm not going to do this yet. I'm going to change my own mind. Everybody that has an account to get an API key should be able to go to this website, planet.com/explorer, which is not going to load because I'm showing it to you live, because it's all slow here. Oh, I got to log in. All right. This is the browser interface to the API we're about to use. I'm starting here just so we can look at things, because when we're talking about spatial information, it helps to orient your brain by looking at literally a picture of the Earth. So you all should be able to see this if you go to planet.com/explorer and log in. And what it's going to do is allow you to zoom in and search for data through the browser. So I talked about the CC by SA data. Planet has this, sorry, that was loud. Planet has this thing called the Open California program, and that's what we're going to use today. You can read more about it on developers.planet.com/open, which I wrote. But basically the idea of the Open California program is that all of the data in the state of California is released as CC by SA data on a 2-week delay. So Planet, remember I told you, does this daily cadence Earth observation, so you can get everything starting 2 weeks ago, going back in time to the beginning of our data collection for California. And all of that is CC by SA, which means if you're an academic or a student and you want to do research, you can do everything you want with that data, publish it, no problem. If you're a developer or a ML AI, not nerd, MLAI person, and you're interested in that sort of thing, you can develop your programs or your algorithms using this data and publish it at will. Or you could learn about it in a tutorial like today. So this Explorer interface, this browser interface, I'm going to zoom into California, because like I said, we're talking about California data. But it's going to let me tell you a couple concepts, keywords that we're going to use later. So the first thing we want to do if we want to search for data, and this is not a planet-specific term, this is a term that applies across anything you do with geospatial data information, we want to define our area of interest. So, as you would expect, it's the area of data that you're interested in looking at. The AOI is the bounding box of the part of the Earth, the footprint on the Earth that you want to get information about. This is how we constrain searches, for example, or constrain searches or filters, that sort of thing, when we're acquiring or looking for data. So we're going to define an AOI here in Explorer using the tools here. So, is anybody in Explorer, by the way? Hey, cool. All right, so if you want to follow along, here on the right, there's going to be this tool. It says draw an area of interest. You can hover over it and draw different shapes, but I'm just going to do a rectangular one because that's easy. And where do I want to go? I'm just going to kind of zoom in here. I'm going to draw a rectangle here, and it's going to zoom in. So this allows me to begin a search. Now, interest, I can search for data in this area. I'm going to walk you guys through this a little bit because later on there's going to be an exercise where you can choose to use Explorer to visually acquire data yourself. But basically I'm just going to show you the interface. On the left you've got filters that you can apply here. Let's see if I can make this a little bigger. Alright, cool. On the left we've got filters. Up here I've got a date range selected. Remember I told you there's daily data available. It goes back to like, ignore that. It goes back to like 2015, I think, we started collecting imagery, so it's not complete. 2017 is last summers where we started having complete daily coverage. But you can get patchy info back to like 2015. But I'm going to constrain this to the month of, well, that's not good. I'm going to go like the month of July last summer for really no reason. I'm just setting an arbitrary date range. I'm going to let it load some results there. But then I'm going to, in this drop down, you can pick daily imagery. You can also pick mosaics. I'm going to explain a little bit more what a mosaic is later. But essentially it's just a bunch of imagery aggregated and stitched together into a single flat base map. But right now we're looking at daily. I'm going to set some filters here. You can click this. I'm interested in information or data that doesn't have much clouds. So let's say less than 30% clouds or less than 31% clouds. I don't want information with clouds in it because that's not very useful to me and it's not pretty. So I'm going to ignore that. I want information that covers my area of interest at least halfway. So I'm going to set my coverage 51 to 100%. All of these little sliders I'm demoing here in Explorer right now because in a minute when we start using the API, you're going to be specifying these filters in programmatically. So this helps you understand visually what they're doing before you apply them in Python. And also, if none of this makes sense or it's boring, feel free to let me know. I'm going to ignore these filters for now because I don't really care about them. But if you did care, you could set those as well. And then the last thing I'm going to look at is the source. So something to note about imagery that you're getting out of the Planet API. It's going to be categorized based on item and asset. Let me see if I've got that on the slides. Yep, item and asset, just so you know what I'm talking about. The item is basically going to be the type of sensor that it was captured with. The asset is going to be the type of image that came from that sensor. These words are a little confusing, and the reason I define them is they're planet-specific, not Python-specific, planet-specific. And when you're searching for planet data, you're going to come across the words item and asset a lot, and it's just a quirk that you have to learn. So an item is going to be this type of sensor that captured it, basically. It's a catalog entry in our giant data catalog. The satellite sensors that we have are these sources here. So PlanetScope, when I talked about these tiny satellites that we call doves, the sensor is a PlanetScope sensor. So PlanetScope is talking about these satellites. 4-band, like I told you earlier, is going to be red, green, blue, and near infrared. 3-band is going to be that visual data that's just red, green, blue. So that's the two kinds of item that you can get out of this satellite. We have other satellites that you can get information on. Like I said, you can get Landsat information here. You can get Sentinel information here. But then Planet also owns RapidEye and SkySat satellites. They're just different types of satellites. RapidEye and SkySat don't have the global coverage on a daily basis, so I usually ignore them. But they're cool. But right now, I'm going to look at 4-band PlanetScope data. That means I want to look for data that has red, green, blue, and near infrared, comes out of one of these, and covers my area of interest, doesn't have much clouds, meets my time box of July 2017. So these are the filters I want to apply. I'm going to let that go. And what's going to pop up here on the left is going to be that data. July 31st looked like that. July 30th. Takes a minute to load, looks like that. Should load completely, it tells me it has 100% coverage. I'm not going to click a lot of them because this is so slow on this Wi-Fi, but basically what that lets me do is preview every single day that matches my results. For example, look, we've got, actually, July in this area wasn't very cloudy at all because we've got imagery almost every day. 5, 4, 3, 2, 1. Oh, the 20th must have had some clouds because we skipped it here. The 18th had some clouds. That's what you can see there. But let's say I want to download this imagery here. Let's download the 31st for no reason. I'm going to hover over it. I'm going to click this button, gray button on the right. Tells me how many images are in this stack. And then I can hover over each one. Notice that one image doesn't completely cover my area of interest. It takes 2 in this case to cover it. This is because when any satellite, a dove or anything, captures imagery, obviously it's not taking one seamless video, it's taking pictures. So just like if you're taking a picture in your phone, what's it called, where you like do a mosaic and stitch it together, that sort of thing. Anyway, it's going to take a bunch of images that slightly overlap with each other and they're side by side. And that's just how image collection works. So if you want to work with a large area of interest, you're probably going to end up stitching images together. So when I said I was going to tell you what mosaic means, that's what we're talking about here. You've got those images that are adjacent, taken by the same sensor at the same time, well, within a few minutes, but they are not yet stitched together. That process is called mosaicing. We may also call it compositing. You're compositing images. So here in this Explorer interface, July 31st takes 2 images to cover my area of interest. If I wanted to download them, by the way, there's another set of images on July 31st that, if you can go down here, they barely cover. Well, this one barely covers, and then this one covers at a different angle. They have a different timestamp. But let's look at this one here. If I want to download it, oh, that's not what I want. Sorry. If I want to download it, I go down here and I click this Order Items button. It's called Making an Order, which is confusing, but you make an order in order to download it. And what you can do here is select which of these pieces of imagery within your area of interest you want. You type in a name for your order, and you click place order. It takes a few minutes, and then it pops up a message if you're still looking at Explorer. It also sends you an email saying your order is ready to download. The reason this takes a minute is all of this imagery is stored kind of in cold storage. It's not immediately hot and ready to download. So it activates it and makes it accessible on a public download link, which is a temporary link, and then it tells you where that is. The reason I'm telling you all that is when you use the API, you're going to have to do the same thing. Activate imagery, make it downloadable, then access the download link. All right. Yes. Oh, good question. Analytic is going to be, well, actually it says it down here at the bottom. Good, so I don't have to remember. Analytic is going to be orthorectified, which means it's corrected for the position of the Earth that it's on in the coordinate reference system. And it's going to have that four bands of information. Basic is just not corrected yet, not orthographically corrected, orthorectified. So if you want to do that yourself, you would get the basic. For our purposes here and for my purposes on my own, I never download the basic. I never get it. I just let the post-processing take care of the orthorectification for me. Yeah. Any other questions? Okay, it's been about an hour. Would you guys like a break now or go on and work a little bit with the API? All right, I was going to say first person to speak gets to vote, so cool. We'll do a little bit with the API and then we'll take a break. I think they'll like put out the snacks and stuff. So those of you that have the notebook server up and running, let me make this bigger so you can see it real quick. Can you read that bottom line? Okay, good. The yellow shows up. That's the notebook that we're going to use. I'm going to walk you through that just to do an example of using the API to get familiar with getting imagery. I'll leave this up a second so you can navigate to it, and then I'll pull mine up. All right. By the way, I'm not used to teaching a tutorial where I have to stay behind a podium. This is very weird. I'm used to walking around. Oh, is mine running? It is. There it is. All right, ignore the fact that this is a Python 2 notebook. It's just because I wrote it like last year, but you can totally do all of this in Python 3. Is that legible? Let's go a little bigger. So things we're going to do. Oh, by the way, raise your hand if you need a few more minutes to get this notebook up. All right, I'll wait. I'll talk to you about what we're going to do. What's that? You don't need the data to do this. In fact, this is going to acquire data, which is why it's a good thing to do before you go take a break, because hopefully it'll download while you're using the bathroom and getting a snack. Hopefully. If it doesn't, that's why we have the data. So what we're going to do once you get this notebook up is we're going to define an area of interest, like we saw that I did in that browser interface. We're going to save the coordinates of that area of interest. So what we're going to do is format it as Geo JSON data that we can send over the wire to the API. We're going to set up a couple filters, just like I did in that browser interface. We're going to search for things that match those filters. We're going to activate, which is the step of basically placing that order via API, telling it, hey, I want this data, pull it out of cold storage, bring it to me. And then once it's activated and ready to download, we're going to initiate the download. I'm using requests for this. This whole notebook is requests. If for some reason you prefer like RLib2 or whatever, go for it, but I'm not going to walk you through that. I know satellite data is boring. It's fine. Okay, anybody still waiting on the notebook to get up? Cool, we're ready to go. All right, this is a demo. I'm using an arbitrary location near Stockton, California, because that's what happened when I zoomed in the browser, or in the thing I'm going to show you in a minute to define the area of interest. Could be anywhere. To get an area of interest and get GeoJSON coordinates, I'm going to cheat and use a website called geojson.io. So you can click the link in your notebook, you can type it in. It's slow. Geojson.io is really great. You can do one thing really well with it. You can draw a box and generate a GeoJSON file. It's great. You can draw more than a box. You can draw shapes. Oops. And also great. Everyone here is probably familiar with JSON. Cool. GeoJSON is JSON with location data added to the spec. So you can put data in it just like with JSON, but then the spec also handles coordinates, what it calls geometry. Used to have a nice URL. I guess it's just .org. Yeah. You can go to geojson.org and click through and read the RFC if you're into that. To figure out more of how it goes. But bottom line, what we're doing is putting coordinate information into JSON format so we can send it over the wire. So geojson.io is what I use to generate a square area of interest for this demonstration. I'm not going to make you guys do a separate one, although you could. You could also download the one that I got here. Actually, feel free. Take a minute, define your own area of interest. I recommend something small. Notice how zoomed in I am on this city, because you don't want to get like 1,000 images in your result. Remember to keep it in California so that you can make sure you have CC by SA results. And when you have an area of interest defined that you like, there's a save menu at the top of GeoJSON.io. Save it as Geo JSON. I'm going to give you guys like 2, 3, 5 minutes to do that. Right. Anybody want a few more minutes for this GeoJSON work? Yes. No? All right. Sounds like we're good. Cool. So hopefully you have either defined an area of interest or decided to just use the demo one here, which is fine either way. But bottom line, you want to be able to grab out, excuse me, the geometry. So we want only that coordinate information. Here's my Python line where I'm saving that geometry, that coordinate information to GeoJSON geometry var. This is my bounding box shown up here. You'll notice I have 5 points. 1, 2, 3. Let's make sure I didn't lie to you. Yeah, 5 points defines a box because you've got 1, 2, 3, 4, and then you end at the same place you started. In fact, if you compare the last line of numbers to the first line, it's the same. So if you drew a rectangle, you should have something like this. But basically, go ahead and do that. If you want to use the demo data that's in this notebook, just run that block as is. If you want to insert your own AOI, just replace those coordinates, no problem. Everything copacetic? Awesome. So now let's set up some filters. I'm going to talk you through what this block is doing before I actually run it. But I cheated by writing it out so I didn't have to type it while you're watching me. So first what we want to do, we want to make sure we get images that overlap with our AOI. We don't just want to search every image forever on this globe. So we want to make sure we attach our GeoJSON geometry object, or dict that we just made above. And we want to set up the filter to filter for that. Now, you can go read the API docs later. In fact, highly encourage you to do that. But you can just trust me that this is the name of the, this is the JSON keyword that you pass to set up a geometry filter. It's camel case, it's ugly, geometry filter. Then you just stick your coordinates in there. So this is going to set up a filter to only search for imagery in our area of interest. Now let's set up a date range. Date filters are kind of a pain because you have to use the long date format string. So you can copy this one if you feel like searching, what am I doing here? Everything that happened on like August 31st, 2016. So I've got a 1-day window I'm looking at. You can expand that window if you care. You can change the dates if you want. I did not bother specifying specific times, but if you really felt like it, you could. And what we're doing is looking for date acquired, so captured by a satellite on this, or within this window, this date range filter. That acquired key is a metadata field value attached to the image itself, which is nice. But yeah, that's pretty straightforward, other than the fact that it's ugly. And let's also set up a cloud filter, just like I showed you in the browser. Let's only get things that have less than 50% cloud coverage. So less than 0.5. That's the annoying way of setting up a filter here. We're going to call it a range filter over the field cloud cover specifically. And then the very last thing we're doing in this block is just combining all our filters together so that they all apply inclusively, not exclusively. So it's like the cloud filter and the geometry filter and the date filter all apply together. So we combine them in what we call an AND filter. All of these filters are defined in the documentation. Don't worry, you won't memorize them. You'll just go look it up every time. That's what I do. But I'm going to run this. See if it ran. Okay, it ran. So now I've set up filters. So far I haven't done anything yet. I've just saved a bunch of text in JSON. So let's actually do a search. So I already talked to you about items versus assets. For this demo, I'm going to search PS scene 4-band. So I want that 4-band PlanetScope image, and I'm going to get analytic. Now, again, you can go read the documentation and find different types of assets. If you only wanted the RGB image, it would be an item type PS scene 3-band and asset type visual. Don't worry, I don't expect you to remember that. You should be able to click this link and it'll load and tell you all the different item types and asset types that you can request. Actually, that's the old documentation. I should give you a link to the new documentation. That's fine. But now let's actually set up the search. Now, before we do this, any questions about what we've done thus far? Everything make sense? We haven't really done anything yet, so it should make sense. All right, so we're going to pull in what we want, which is requests, like I said. If you're using the Jupyter Notebook environment, your API key is already there because of that Docker run command you did. It's already there as an environment variable for you to access. So you don't need to type it in here. I don't need to see it. You don't need to see it. Just access it like so. Can you see this code? Well, you can see it on your own screens. All right, so we're going to pull in our API key to make our GET request. We're going to specify that we want PS scene 4-band, so we want a planet scope 4-band item type. We're going to set up our request object. If you recall when we were looking in Explorer in the browser, that drop down, you can select daily imagery or 1-month mosaic or 3-month mosaic. Those are the different intervals of data that you can request. So here I'm going to define day as my interval because I want daily imagery. We're going to make a list of all the item types that we want. In this case, we only want PS scene 4-bands. And we're going to apply our filter. Then we're going to just set up a request. And then we're going to, well, let's look at it here. So let me run it, see if it works, see if I get an error. Great. This is what you should get back, something like this. If anybody does not get this, yes, what's up? Okay. It does? Then make sure you are using the correct environment variable name here. It is. Make sure, print Planet API key here, make sure you've got something there. Then make sure you're putting Planet API key here. And you're getting an error? Okay. Everybody else, were you able to get results or error? I want to know. Results? Cool. Error. Couple errors, couple results. What error? Yeah. It's a string, but it got injected into your Docker image with that run command. If you're not using Docker, yeah, it's just a string. Yeah. API key between quotes. Yep. Yes. Oh, yep. Those of you that are getting errors, you probably ran the run command, using the square brackets. Make sure you've only got single quotes and then your API key, no square brackets. I need to update that command in the README because it's very confusing for people who aren't sure what it's doing. Yeah, what you want to do is Control-C, or I don't know how you do it on Windows, but you want to kill that run command and then rerun it. It won't take but a minute, and make sure you delete the brackets the second time you run it. Oh, yeah, you know what? Actually, just for now, just put your API key in the code block and save it. Never mind, that's dumb. Yeah, we'll get there. Quotes good, brackets bad. All right, yes, of course. Just paste your API key in there. It's just a string. We'll rerun your Dockers later. Bottom line, everybody should be able to get a JSON blob printed out. Geo JSON even. Yeah, that's fine. It's JSON. As long as you've got something that's not an error. So what this is going to return is metadata for every image that matches your search. There's probably a lot of images. If you scroll through here, there are a lot of images. Metadata, let me just look at one to show you. It's going to have an ID. Each image has an ID. You could actually dissect this and figure out what day it was taken and what time it was taken. That's basically what its ID is. It's going to have links to itself, permalinks to its metadata. If you have your API key, you can actually load this thumbnail and get a preview of it. Let me see. You should be able to do this in your browser and log in with your password. Let me see if that works. Oh, crap. Okay. Don't do what I do. That's very bad. There, thumbnail. Yeah, so you can log in with your username and password if you feel like seeing that thumbnail. You could also make a GET request with your API key, that sort of thing. So that's going to be part of the metadata, that permanent thumbnail URL. All images have permissions on them. You really don't need to worry about these because if you can see it, your account has permission to see it. But yeah, permissions is also a way you can see all of the asset types that you have access to here. So assets dot whatever, that whatever is going to be the asset type that you can download. Then scrolling on, it's going to tell us some more about this information, exactly what time it was acquired. So what timestamp it came out of the satellite camera with, basically. The satellite itself was 0C43. Every satellite has an ID, which I think they should have names, but whatever. Sun elevation doesn't really affect anything I do, so I ignore it. Pixel resolution is always the same for a dove. It's going to be 3 meters, but that's good to verify. How many rows are in it? EPSG code. This is the the coordinate reference system that you can go look up if you care. Item type, instrument. A lot of this stuff I don't care about. Came out of Planet Scope. Doesn't have any anomalous pixels. Sometimes it might have an anomalous pixel. Updated. The last time it was updated, even though look, it was acquired in 2016, it was updated last October. Post-processing gets run on Imagery and creates new types of assets occasionally, so it could get updated. But it's still, the original image itself was from 2016. This has 0 cloud coverage, that's pretty cool. And it was published to the catalog. If you compared timestamps, it would probably be like a couple hours later. And then here's going to be the coordinates of its bounding box. And then we see ID, that's another image. So all of these are images. All of these are metadata on images. Now just for the sake of this data, I'm just going to extract one ID arbitrarily. If you were actually looking for something specific, you wouldn't do this. But I'm just going to pull the first one, basically. Well, first let me pull all the IDs. These are all the IDs. So if I counted these, that would be the number of images that matched my search. But for the demo purposes, we're just going to like pick one of these. Everybody following? It's all good so far? I don't want to like run code blocks and run away with you. All right. So let's just grab that first ID and use it as our demo to activate and download. So you can see I'm just grabbing the first one. It has the URL already in here. Basically, we just stick item type in here, asset type there, I'm sorry, item ID there, and this format is in the documentation. Don't worry about remembering it. Just copy it out of this code block. So what we want to do is we want to get specifically the metadata for all assets that belong to this ID. Now you remember I told you we're looking for analytic assets. Every image captured by the satellites has multiple types of assets. You've got that basic. He was asking me about basic versus analytic. You might have visual also. And there's a couple other things. So there's going to be multiple assets for this same capture over the same piece of the Earth. So let's look at all of them. So here's all of the asset types that you can get here. Basic analytic RPC NITIF, analytic XML, which is going to be a metadata file, basic analytic DN. All of these are documented. Not all of them do I know what they do, so don't ask me. But what we want is just an analytic, straight analytic, which is here. Anything else of interest that I could tell you about here? Not right now. So don't worry about it. We're just going to look for that analytic. So this confirms that that asset type does indeed exist for this ID, which it should because we searched for it. So let's activate it. Let's place our order, have it pulled out of cold storage. First, let's check its status. Somebody else has already run this in this room with the demo. So usually this is going to say inactive the first time you run it because this piece of data is not yet active for downloading. However, somebody in here is working ahead, which is awesome, good for you. And you've already run the next step, which is going to activate it. So that's what this does. We're going to, well, 2 more steps. We're going to pull out the links to actually trigger the activation, which is just buried in that Geo JSON. And then we're going to actually do a GET to request it, which I shouldn't have done it again because it's already active, but that's cool. Excuse me. This is just going to give us the status, which we already know, and it saves the link in a JSON blob. Seems like everybody's good. I'm not going to talk you through what's going on here. All these code blocks are doing is making requests, parsing the responses. The response body formats are documented, so you can go read about it if you care. Bottom line is the process we're doing, activating, then downloading. So I'm actually not going to trigger this download. Y'all do it if you want it. I'm not going to do it because I don't need to download this and I won't bother sucking down the bandwidth. But if you run this last code block, it's going to download whatever arbitrary image ID you just activated. So this is a thumbnail of the one I've got going on here. That's a really basic introduction to the API and searching for data. With that, I am going to not break us, but stop for a break. And let's say well, questions first, then break. What's up? Yeah, let me see. Here, uh-oh, maybe my notebook's bad. What you're going to need to do, you can't skip running any of the previous ones. You have to run those first. Still give you a key error? No? You're running it out of the notebook, right? All right, how many people got a key error on location? What? Oh, because you're doing different ones. Yes, if it's still activating, right. You have to wait until that status says active. So step 8 has to print active before you can run step 9. Yes, thank you, because not all of you are using the demo ID. Those of you that are doing data that's not already here, yeah, cool. Now, normally, you're not going to sit here and rerun the same line. If you're writing a script to do this, you're just going to have a callback and keep checking it. But that's the process. Gotcha. Any other questions? Okay, I'm going to say let's break for like 15 minutes. Those of you that are waiting on a thing to activate, if you want to chill here and then kick off the download before you leave, that's cool. But let's do like 3:05. Most everybody's back. Not quite. I'm going to give it like 1 more minute, just so everybody gets back. Yeah.
So how do I change this to a normal color? So you mentioned that.
So what is normal color for near infrared?
About 3 bands.
Then you download a 3-band image.
Oh, so this is the 4. So
Yes.
we don't know.
Only if you want a 3-band image, but you don't need it necessarily. I mean, it's up to you what you want.
Okay.
Yeah.
Thanks.
No worries. Okay, we're going to start back up. People will trickle back in slowly from break. Any questions? Any problems downloading? If you do not have some kind of GeoTIFF image, whether it's from the demo data or downloaded just now, raise your hand, please. Okay, good. Everybody has some kind of GeoTIFF image, right? Okay, good. I'm going to take silence as a yes. The reason I asked that is because let's write some Python to learn about this image. Is everybody ready for this? I know some people are still, looks busy. All right, I'm going to move on. If you need me to stop, yes, just raise your hand. Activate could be like up to 10-15 minutes. Sometimes it takes a while, unfortunately. Still not activated? If it's not activated in like half an hour, let me know, but it should work. Then I'll just check our API and see if it's down, which I should be on call right now, but thank you guys for getting me off call today. But if the API is down, I wouldn't know. All right. Yes, let's use Python to inspect one of those GeoTIFFs. So what we're going to do, first we're going to inspect it, we're going to learn a little bit about it, and then we're going to visualize it in a notebook. So in your notebook server, in the running notebook thing that you did with Docker run, navigate to this directory, this getting to know sat imagery directory, which I will pull up. And we're going to start with inspecting satellite imagery. Yep, no problem. All right, if this doesn't exist, y'all need to do that pull down the latest master step from my very first slide today, because I put it in there Friday at like 6 p.m. because there's nothing like last minute work. So go ahead and just get pull origin master or whatever you need to do to pull down the latest master. Yeah, no problem. What link? Well, go in your repo directory where you cloned it. I don't know where you put your directory. And then wherever that is, you're going to pull latest master. So however you prefer to do that, whether it's Git GUI or command line. So once you pull that down, you shouldn't need to restart your Jupyter server. It should show up if you just refresh the tree. I will wait a minute more. Once you do have that, I feel like this whole room got brighter. Once you do have that, you should have, let me double check this real quick. I don't remember what's in that demo data. Right. In the demo data directory, there's an example.tiff in data/raster. If you want to stick that in here, you can. I can't remember if it's in the Git repo or not. I can check. Okay, disregard, it's in the repo, you're fine. So the data we're going to use for this next step is going to come with the everything that you cloned out of that notebooks repo. So when you're able to, and when you've pulled down the latest master, go ahead and open the Inspecting Satellite Image notebook. This is a Python 3 notebook. If you are following along in your own local environment, like using Anaconda or whatever, Python 3 is good to go here. All we're doing is messing with Rasterio, so you should be fine. But if you don't have, well, you should have, even if you're not using the Docker, you should have the repository with the example.tiff, but if you don't, use any geotiff you want here. Make sense? Mostly? No, not at all? Okay, cool. Awesome. So far we've learned how to, well, we've learned what satellite imagery is like. We've learned a little bit about Earth observation, and we've figured out how to search for, filter, and download satellite imagery, and or how to acquire it in other ways like SneakerNet from a USB key that somebody brought over to you. So let's take some of this data and learn a little bit about it. So we're going to use this library called Rasterio. I mentioned it earlier. Anybody here ever heard of it before this class? Awesome, that's super cool. Just because I'm curious, how did you hear of it? Google. No, nobody else? Well, you've heard of it, which is cool. But yes, Rasterio is super great. It wraps around GDAL, which you may or may not have heard of. GDAL itself is super great, but it's kind of a pain to use from Python. Its native bindings are not super Pythonic. Rasterio is a lot more comfortable to use and a lot more friendly to a Python programmer. Also, Rasterio, tangent. Anybody used NumPy before? Most people here I figured have. Good. Rasterio is very familiar if you're familiar with NumPy and NumPy arrays. Everything in Rasterio is essentially represented as a NumPy array, which is super nice. It's just data. It just happens to have location information attached to it. So first thing, let's open a geotiff using Rasterio. In my examples here, I am referencing this example.tiff that comes in the repo. If you're working out of the repo, if you're working from the Docker image, you should be fine. If you want to use your own data, that's cool. Just change the path here. Does anybody mind if I shut this door? No? Good. Awesome. So I'm going to run this assuming we're using example.tiff, but again, you can put in whatever you want here. So all we're doing right now is reading it in. Rasterio.open is opening this file. So let's learn a little bit about this file using Rasterio. Let's get the bounding box. .bounds on the file that we've opened. It's going to tell us what the bounding box is. Now what this is, it doesn't really matter, but what it is the coordinates for each corner. The left, bottom, right, and top, which gives us the area that this image covers. This specific example.tiff that I'm opening here, yours might look different. But that doesn't make much sense to us, so let's get the dimensions. How big is our image? This is going to use map units, so depending on your coordinate reference system or your projection, your units might be different. For this example, it's going to be meters. Most of y'all probably, it's going to be meters as well if you just got data or if you're using the demo data. So what we're going to do is we're going to just do basic math on these numbers here. We're going to take the difference between the width and the height, figure out what it is. So this example.tiff has a width of 5,976 meters and a height of 7,269 meters. Hang on. Okay, that's better. So it's about 5 by 7 kilometers on the surface of the Earth, this image this particular example.tiff. But that's nice, but it doesn't tell us much since we're looking at an image, like how many pixels do we have in this image? So what we're going to do is, pull width and height here. Instead of pulling bounds and doing math, we're going to directly access these width and height attributes. And that's going to give us the pixel dimensions. So using that information, so now we know how wide our image is in pixels and how wide our image is in meters on the ground. So you can probably guess what we can learn next, especially since it's already in the notebook. How many meters to a pixel? The reason this is an important and interesting question is the number of meters or units to the pixel is the resolution of this image. So if you hear people talking about 1 meter resolution, 10 meter resolution, that's how many meters go into a pixel. So here, let's just do some math. We've got 3 meters to a pixel. Width and height is the same. It would be weird if it wasn't square, but just in case. So we've got 3 meters to a pixel, which is good because I already told you these satellites capture 3 meter resolution. So we're just confirming that we know how math works and it does what we expect. Does that all make sense so far? Cool. All right, let's figure out what that coordinate reference system is. You remember we opened a file in QGIS and looked at it? Let's get that information here. Same thing we saw in QGIS. It's an EPSG code, but you can get it here. It's a lot faster. Nothing very interesting we're going to do with it right now, but you could use that information to do more. Now we're going to do something a little bit more complicated. Anybody here, raise your hand if you're not using the Docker thing. Okay, y'all might have different Rasterio version, in which case this is going to be different. This is going to throw an error for you. If it does, let me know. I used to have both versions in here. Anyway, what we're going to do is we're going to take advantage of the fact that this data set, this example.tiff, has a coordinate reference system attached to it, and we're going to ask Rasterio to compute the coordinate for that top left corner, not just the position literally on the Earth or the number of meters it is away from another point. We want the coordinate. So we're going to use this transform function, and transforming is just doing math on a specific point based on the coordinate reference system. So those of you who get an error here, I think if you change you got an error? Yep. Transform, do dot affine, A-F-F-I-N-E, and I believe the params are the same. Affine, oh, I should type this out. Oh, it is, there you go. You should be able to do affine times foo, etc. Whoops. That wasn't good. I just completely deleted. What? It doesn't work. Don't. Oh, don't delete. Thank you. Don't do Vim shortcuts in a notebook. I do this all the time. It's like, Dee Dee, your cell's gone. No, Control Z didn't work, but thank you. Oh, Z? Oh, okay, thank you. I don't use notebooks enough. But yeah, basically what this will do, if you're able to run it, whether you're using Transforma or Affine got retired, it's going to compute the coordinate for that top left and bottom right corner, which gives you the extents and coordinates of your area, your area of interest. Now that I've walked you through step by step getting all of this information, I'm just going to show you that you can do access the meta attribute on the file object or the opened file object, and you can get all this stuff. Also gives you a little bit of more information that I didn't tell you yet. Worth noting, the D type, which is the array type here. We'll use that a little bit more later, so I won't talk about it much now. The driver that it was used to open it was GDAL's GeoTIFF driver, which makes sense because it's a GeoTIFF image. If it's a different type of image, the driver would be different. And the count 4 means that this particular example.tiff has 4 bands. Count is referring to the number of bands here. Everything makes sense? All right, cool. So let's talk about bands. Any questions before I talk about bands? All right. All right, so yeah, that was neat. We looked at some metadata, but that's kind of boring. Let's do something specific to a geospatial raster. All right, the number of bands. Like I said, we already know there's 4. Let's list them and their indices. Yay. As you might expect. Actually, no, as you might not expect. Notice that our indexes start at 0. Don't start at 0, sorry. They start at 1. This is just a Rasterio convention. I think it's a GDAL convention that they're inheriting, but basically it makes more sense. If you want to talk about band 4 in English, then you want Rasterio's reference to band 4 to match up. You don't want to have to do zero-based indexing in your head. Make sense? All right. So, because I told you, or if I hadn't told you, you'd go read the documentation, you would know that the Planet Scope 4-band data, the band order is BGRN. This is just some traditional trope. I don't actually know why that's a normal band order for 4-band images, but I'm sure there's a reason. So let's go ahead and assign these bands to variables. So we're just going to read each band here by index. You could also do it this way. We're just going to pull them in. In being near infrared, I'm just calling it NIR here to be easier, but just to let you know that's what we're talking about. So I keep telling you about how rasters are essentially grids of pixels, and this is just a little visual reminder of what we're talking about here. So think about an image, it's a grid. If you zoom in enough, you have that pixelated look. And then if you think about it in a simplified way, it really is just a grid of pixels. Each pixel has a single value. Pixels that represent equivalent data have the same value, even if they're not in the same location. That seems very basic and straightforward, but it's the essential concept to get your head around. And the reason why that's so essential to understand is in Rasterio, bands are just read in as NumPy arrays. It's just a grid of data. So think about a 2-dimensional NumPy array, it's just a grid. So that makes it really easy to work with and do math on and get information out of. And then Rasterio, because Rasterio knows the coordinate reference system, it can do transformation. You can still hang on to that geospatial quality, that location that location aspect of your data while manipulating it as a NumPy array without really thinking too much about the fact that it's a GeoTIFF versus a NumPy array. Makes it really nice to work with. Well, I already gave away the answer to this, but anyway, how many dimensions does a raster have as a NumPy array? 2. Somebody want to explain why? They're like, this is only day 1 of SciPy. I'm not ready to explain this. Right now we're talking about the two-dimensional array essentially being rows and columns. So think about it versus a cube. We're just talking about literally a flat image. Yeah. So that's why. It's just like the, I'm pointing at my screen again. It's just like the image on the left. It's just rows and columns of data. It's just flat. So it's always a 2D array. So let's just look at the summarized array, which is not very interesting or useful to us. But if it printed the whole top row, it would be however many pixels wide that we saw earlier when we computed the pixel width. So that would be a lot. And then there's as many, so there's as many columns as the pixels wide, as many rows as the pixels tall, if that makes sense. Each one of these is a pixel value. So 6891 for the blue in the rightmost pixel in the top row, top right corner of this image. Doesn't mean much to us yet, but later we're going to figure out how to understand more about it. But let's use NumPy itself to get some min and max values just to see the range of, for example, blue in our image, like how big is our range. So what I'm doing here is I'm pulling in NumPy itself just so I can use a min and a max. A min and a max, if you're not familiar, is just going to give me an array min and an array max. So because it's a 2D array, I need to use array min and array max. Yay. So again, this still doesn't really tell me too much other than proving that we can manipulate these as easily as we could any other NP array. Let's do something slightly more interesting. So putting together what we've done so far. Let's walk 2 kilometers in and 2 kilometers down from the top left corner, which is going to be east and south. And let's get the pixel at that specific spot. So because we want 2 kilometers, we're going to use our map units of meters. So we're going to do 2,000. We're going to add 2,000 to the leftmost corner, subtract it from the top. So we're going 2 in, 2 down. And then we're going to grab the pixel at that index and print its value for every band. Now remember, SatDat is our entire image that we read in. Then we read each band out of that, but SatDat has 4 bands. So, again, it doesn't really mean much now, but the fact that we can get a value there confirms there is a pixel there. It doesn't have trash data. It has actual data for each value. And we know exactly what it is for each band. Is everybody able to do this who wants to do this? Cool. Questions on this? Yeah. Yep. That is correct. Yes. These, when we use the transform up here, these coordinates are actual on-Earth coordinates based on the fact that Raster knows that it's EPSG 32 blah blah. So to briefly take you down the projection rabbit hole, that's a UTM projection. I think it was UTM 11 North or something, which means this is going to be 544,000 meters, I think, east of the west boundary of this defined UTM 11 zone. Don't quote me on that. It's been a long time since I remembered how they work, but that's basically, it's describing an actual defined place on Earth, a knowable place. So you can use transform on the map's coordinates against the known CRS to get the knowable place on Earth. Does that make sense? That was a little complicated. Okay. Other questions? Yeah. That's a really good question. The raw information, I couldn't tell you. What I can tell you is that ratios between these measurements are where we can get interesting information. I actually don't know, like, what is that a unit? What is it telling me? And different processes can normalize it against another scale, so it kind of means nothing. But processing it or comparing it to other values is how I can get information out of it. Another question. All right, I thought I saw a hand, but no. All right, so we used Rasterio very briefly. My main purpose there of that little exercise was to, number one, let y'all get a little bit of time becoming more literate in Rasterio itself, which is a really great library, even though we didn't use it that much yet, but also to recognize how easy it is to think of a raster as just a NumPy array and a bunch of numbers, and then start thinking about how you might use that to do more interesting things. All right, so let's go to the other notebook that's in the same directory called Visualizing. So we're going to use, anybody use matplotlib already? PyPlot? Cool. We're going to use PyPlot to visualize this image in our Jupyter notebook. So we already used Rasterio, we inspected it, we learned about it, we figured out, oh yeah, it's just a grid of pixels, it's easy. It's a multi-dimensional array, no problem. So matplotlib is really good at plotting arrays of values, so let's do that. So we're going to use the same example.tiff here, or your own image if you want. I'm going to pull in Rasterio as well as PyPlot. Excuse me. Sorry. Still working with 4-band imagery because that example.tiff is, and I think all of you probably also have 4-band. So this is the same step from the last page, opening our file. Why is it taking so long? Okay, good. We're going to load the bands. This time I got lazy. I just called them BGRN. All right, first thing we're going to do. PyPlot will very happily plot a 2-dimensional array for us, so let's do it. There's our blue band for this image. Right now I didn't assign a specific color map to it, so it just kind of has arbitrary colors, but it looks good. I'm going to take a minute. For anybody who hasn't worked with PyPlot, this might seem magical, but all it's doing is displaying the values and then coloring them, or displaying the pixels in their grid form and coloring them based on their value, so higher, lower, and it assigned an arbitrary color map to it, you know, farther up one end of the color ramp or not. The axes labels here kind of don't mean anything because our raster is not a nice uniform grid of progressive data. It's just like scattered. So you kind of should just ignore PyPlot's axes labels here, if that makes sense. It isn't too confusing. So does that make sense to y'all? All right, I see heads nodding. Let's plot another band, but this time let's use our own specific color map. If you haven't worked with color maps in PyPlot, you can copy this URL and look at it, and you can just pick your own favorite one by name. There's a lot of pretty ones. But I'm just picking one here. What I'm doing, I'm plotting G, which is what I called my green band array, and then I'm setting the color map to be this thing called GIST Earth. Felt appropriate. It says GIS and Earth in it. So it's green. Yay. So that's the green band values. Again, you can see we're looking at the same terrain. It's just we're looking at different values here. But basically, there's not much else to see here. But I do like how easy it is to display a raster in a Jupyter notebook when you remember that it's just an array. It's kind of magic. All right, let's do some more magic. Let's put a color bar on this and use another color map because I like color maps. All right, so we've, this time I'm plotting, by the way, R, the red band here, array. This time I put a color bar here, so I know my red band goes from 0 to like 19,000 or something. If you recall in the previous notebook when I was getting the range, I was using like Amin and Amax to get the range. If we compare this to that for the red band, then these values are going to match up. Like our color bar is showing that range. Make sense? Cool. I like a SciPy crowd. Y'all can follow this. It's great. And the last thing is I'm going to take off those axis labels because, like I said, they're useless. And let's plot the near infrared band with yet another color map and a color bar. So there you go. So now it's beginning to look actually kind of useful. Like the axis labels, I don't like them because they make you confused as to what you're looking at. But now I can see like, oh, my near infrared values go from here to there. This is what my terrain looks like. This is the shape and orientation of my image. This is cool. I can actually use it in a notebook when I'm writing some kind of data analysis. But that was just a really quick walkthrough of the type of things you can do, some of the type of things you can do with Matplotlib and PyPlot. I don't use PyPlot very much beyond basically this level of facility, like I stick rasters in notebooks. Some of you, I'm sure, do a lot more, so I would love to see if you guys do some cool things with satellite imagery, what you've got going on. Like, please email me. By the way, everybody get my email before you leave. Please email me, show me. That would be really neat. Any questions here? All right, hang on a second. Okay, we are a little ahead of schedule, which is actually really good because that gives us more time to write other code. But I already did a check-in. You guys say you're fine, so let's move on. All right, the main thing that's remaining, I wanted you guys to have at least an hour and a half on this. And what we're going to do now, and this is great because there's only one of me, there are in-class exercises in these directories. Go in the notebooks, go to in-class exercises. I've got 3 different things here. Each folder is going to have 2, each of these like bandmath, generate, and DVI, mosaic and masking, each of these bullet point directories has 2 files in it. One says key in the name, one does not. You probably can guess that the key one has the answers in it and the other one does not. What you're going to do is open the one that doesn't say key and try to fill in the code blocks until they run and give you the information you want. I'm hoping everybody can get through all 3, and if you guys are great, you'll probably get through it in 30 minutes and leave, and then we can all go home early. But if you don't, take it home for homework. What these 3 in-class exercises are doing is taking the very basic Rasterio and Matplotlib concepts that we just learned and applying them to actual analysis. And instead of making you all frog march through the same one, I'm going to let you do it on your own, and then I'm going to be walking around for the next hour and a half. Does that make sense? All right, cool. You can pick whichever one you want to start with. They're not in any particular order. So pick whatever sounds interesting to you. Highly encourage you to use your own data if you got it. Otherwise, this is where that demo data is going to come in handy. The demo data drive that was going around, there's going to be data/raster/in-class exercises, and then there's a directory for each one of these. Any questions before I step away from the mic? All right. So now you're on your own. Have fun. I'm going to, no. But I'm here. Put up your hand. I'll walk around. Otherwise, feel free to work together on your own. And by the way, thank you for being an awesome class. I'll come back in a little bit and wrap up and give you guys some more links and information. But that's basically it for the listening to me. I'm going to go ahead and put the last slide up since some people want to leave. There's my contact info. There's Dana's as well. You can email her and tell her get well soon. But the website's there, or the website there has tutorials that you can use. A lot of the stuff you're doing here is based on content from that site. All of the API docs and the API references up there. That's the GitHub URL. But my email address, somebody was asking, is it okay to email me? Yes, yes, please email me. I would love to hear from you. Any questions you have, definitely reach out. If you want to leave, that's cool. If you want to sit here and work, that's cool. I'm going to hang out through the end of our slot. If you have any questions, just put your hand up. But basically, thank you all for coming.